Okay, I like every topic that touches on climate solutions, and you have to, understand. I'm just giving introductions and kind of a news item sometimes. So I'm reading from Washington Post. I've read from New York Times before, Vox, and so on. You have to remember that these are newspapers or magazines that are not peer reviewed. So I'm not sticking to the rule that I will only read peer reviewed material to you, because when it's important enough and you know the people, the journal or the magazine, newspaper, whatever, you have to have credibility, legitimacy, and salience of the communication that you are reading, either for yourself or I'm just reading to you here from a newspaper, because you may not have read it. So even in scientific journals, even though there are peer-reviewed papers, the journals are not all up to the same standards. The review process is not all up to the same standards. So always keep in mind. And in this topic, also remember that I'm not really a battery expert, but this is really interesting topic. And these kind of headlines often can be called clickbait. So utilities build flow batteries big enough to oust coal and gas power plants. Is that really true? Well, it's a clickbait. So when I see it, I'm a climate scientist. I'm desperate that I will see coal being phased out in my lifetime. I don't know about gas power plants, but that'll be great as well. So I'll click on it, I'll read it, and then I say, well, there's enough credible scientific material that I can trace back to scientific literature, so I will read it. So here it is, how to build a battery big enough to solve the world's energy problems. That's not a new question, but this topic here, flow batteries, is nice, and they have provided a lot of nice figures as well, and talked to many scientists to build the story. So let's just read it from Sapporo, Japan. Ocean winds whip across the beaches, hillsides, and sprawling plains of Hokkaido. There's enough wind energy here for Japan's northernmost island to power itself and export clean electricity to the rest of the country. No, Japan has a very small land overall. They love their fish, which is in the ocean, but they have to go far and wide sometimes to get it. They love their beef, but they cannot grow a lot of it, even milk, chicken, eggs, whatever. They just don't have enough lands, and then they got spooked by the Fukushima disaster in terms of nuclear power, because they also can cause a lot of problems, and Fukushima disaster did. So Hokkaido can't harness all of that power unless it has a way to store energy when breezes are blowing and use it later when gusts die down. So the standard intermittency problem. So the island is turning to a new generation of batteries designed to stockpile massive amounts of energy, a critical step towards replacing power plants fueled by coal, gas, and oil, which create a third of the global greenhouse gas emissions. We talked about this elsewhere, and Japan did go back to coal after Fukushima to ramp down the nuclear relying on nuclear power. I'm fumbling words again. A wind farm in the town of Setana in Japan's Hokkaido island here. Energy produced by such turbines can go to waste if it cannot be stored. So sometimes you're producing more than you can use, and unless you store it, you lose it. Hokkaido is facing a problem that's starting to confront power grids around the world. For the past 150 years, utilities have stored energy in piles of coal or tanks of gas that can be burned on demand, but as countries switch from fossil fuels to clean energy, they need new kind of backup systems that can deliver power whenever someone flips a light switch, not just when the sun shines or wind blows. Sorry for this choppy text cutting here. Most utilities are definitely recognizing that if they are adding renewables, they have to add storage, says Vanessa Witt, a senior analyst at the energy data and analytics firm Wood Mackenzie. After decades of development, the world has figured out how to make wind turbines and solar panels cheaply and at massive scales. They are starting to make a dent in the energy production, accounting for 15% of electricity globally, according to the International Energy Agency. But now a few of the regions that have adopted wind and solar most aggressively are finding some of that energy goes waste because they can't store it right? So another way to think about renewables growing is if new demands for electricity are being met with renewables or fossil fuels, right? It turns out IEA is very optimistic and thinks we will hit peak emissions from fossil fuels very soon. Not everybody agrees, but they are projections anyways. Power companies are experimenting with new ways to hold on to that clean energy from stashing heat in vats of sand. Indians have a problem with W and V, or at least I do. To vats of sand to supersizing the lithium-ion batteries that power laptops and cars. Some 30 miles from Sapporo, the Hokkaido Electric Power Network, HEPCO, is deploying flow batteries, an emerging kind of battery that stores energy in hulking tanks of metallic liquid. Anything that can take energy or heat and keep it and then can be re-released when you want it is a good battery as well. You can also pump water up the hill and then let it flow down, what we call pumped hydro. So all kinds of technologies are used. When you want to store heat, you want something that has high heat capacity so that it may warm slowly but also will cool very slowly. But the technology faces a raft of challenges, including high upfront costs and skeptical financiers. China and Russia dominate the market for vanadium, the metal that makes flow batteries durable and easy to maintain. The supply chain for vanadium is extremely precarious, says Cara Rodby, a battery analyst at the investment firm Volta Energy Technologies. Still, flow batteries are making their debut in big real-world projects. Sumitomo Electric, the company that built the Hokkaido plant, has also built flow batteries in Taiwan, Belgium, Australia, Morocco, and California. So this is not a joke. They are very serious and able to sell it, right? Hokkaido's flow battery farm was the biggest in the world when it opened in April 2022, a record that that lasted just a month before China built one that is 8 times bigger and can deliver as much energy as an average US natural gas plant. So if you can have such battery technology, then intermittency and even peak demands can be easily met. Typically fossil fuel or even gas power plants, which are cleaner than coal or oil, burn other dirty fuels when peak demand increases, and they're called peaker plants, which ramp up the energy quickly when demand goes up, like in the middle of the day or when a winter storm hits and heat wave comes and so on. Looks like flow batteries are finally about to take off with interest from China, said Michael Taylor, an energy analyst at the International Renewable Energy Agency, IRENA, under the UN, an international group that studies and promotes green energy. When China starts to get comfortable with the technology and sees it working, then they will very quickly scale their manufacturing base if they think they can drive down the costs, which they usually can. This is what the power plant of the future may look like. Instead of stashing coal and gas next to the furnaces, they will use electrons to store energy inside giant batteries. You know how batteries work? We'll see in a minute. They have an anode and a cathode. You load up the ions, and when you have electricity need, you connect the two, and then energy flows, and then you have to move the ions back with the electrolyte in the middle. A flow battery system here designed to stockpile massive amounts of energy at a plant on Hokkaido. Obviously, we talked about liquid metal. Vanadium is the prime candidate because you need a metal that easily liquefies, doesn't take a lot of energy, has sufficient heat capacity, and can keep the heat, and all the standard requirements. If the world is going to power itself with renewable energy, it needs to be ready at a moment's notice. So electrons come into play. All power grids have to pull off a delicate balancing act. There must always be about as many electrons flowing out of power plants as homes and businesses are using. That's electricity. If that balance even falters, if that balance ever falters, the community could face blackouts, or the utility could waste money making extra energy no one is using. So supply demand is very critical. To make sure there is always enough electricity to go around, energy companies rely on extra polluting power plants called peaker plants that I just mentioned. They get their name because they only run when electricity use hits its peak. For example, on a really hot day when everybody runs their air conditioners at once. We talked about AI for managing power stations, power production, power grids better. this intermittency and predictions for that, purchasing requirements by utility companies. These are all critical issues on managing the overall energy production and supply. Peaker plants tend to be older, less efficient, and more polluting than other plants. Most of the time they sit idle, but in an energy emergency they dump fuel, usually natural gas, into their furnaces to generate electricity fast. That keeps power flowing steadily to homes, businesses, and factories, but also pumps pollution into the air, and only rich countries may have gas. Most poor countries may use coal for peaker plants. Wind turbines and solar panels don't pollute, but they can't make more electricity on demand. When wind is there, when sun is there, they produce energy. Otherwise, boom, they don't have energy production. They only produce as much energy as the sun and the wind provide, which changes throughout the day or year depending on the weather. One way to smooth out these bumps is, of course, to use batteries to store renewable energy when it's plentiful and use it later when it becomes scarce, as we said. So here is a schematic of electricity output over the course of one day. Without battery, you peak and then you die off as sun comes up, peaks and dies off. With battery, you have a storage power so that use of battery power can occur when production is low in both ends, and you can store power when there is excess and sun is beaming a lot of energy that you cannot use when you capture it. The energy held in batteries mirrors the tanks of gas sitting next to a furnace waiting to be burned, except batteries can send out electricity even faster than a furnace can ramp up, and they don't create carbon pollution. Utilities are already building battery farms in regions that have added a lot of wind and solar power, such as California and Texas. So far, most of these batteries are lithium-ion, similar to the ones in a phone, laptop, or electric car. Because they are already built in bulk for other industries, they have become the default options for power companies. So here is a model of the flow battery system run by Hokkaido Electric Power Network. You don't see many details, but you see tanks and systems which are moving electrons into the liquid metal, heating it up and storing it for later use as batteries. But experts say there might be better options. Lithium-ion batteries are perfect for smartphones because they are lightweight and fit in small spaces. Miniaturization is always important for energy density. Even if they don't last long and have to be replaced frequently, they can be recharged, reused, and serve the purpose. Even Tesla can run on lithium batteries, or many other cars. Utilities have a different set of priorities. They need to store millions of times more energy, and they have much more room to work with. If you think about utility scale stationary applications, maybe you don't need lithium-ion batteries because they don't need to be light. If you are supplying energy by batteries for cement or aluminum or steel, then you don't have a constraint of a small battery. You can build as big a battery as you need. You can use another one that is cheaper and can provide the services that you want, like, for example, vanadium flow batteries, said Francisco Boschel, a researcher at the IRENA that we mentioned before. The flow batteries then, to power cities with renewable energy, you need bigger batteries, monstrous batteries. Here is again, I don't know why I put the figure back in here, just a screw up. Utilities are already building batteries in battery farms in regions that have added a lot of wind and solar power, such as California. Oops, I already read that, didn't I? Okay. But experts say there might be battery power. What did I do? Yeah, I just went back by mistake. Okay. Energy held in the flow batteries at the Hokkaido plant mirrors tanks of gas waiting to be burned, but it doesn't create carbon pollution, as we said. So there is the grid above, but there is the flow battery. Inside a sprawling 2-story warehouse, HEPCO, the Hokkaido company network, the HEPCO network is storing electricity in 130 gleaming steel and plastic tanks. They can stockpile enough energy to power more than 27,000 Japanese homes for 4 hours. Each 10,000-gallon tank holds tiny particles of metal vanadium which float around in water. This metallic soup holds the key to hoarding energy in massive quantities. So it's not liquid metal, it's just powdered vanadium floating in water. Vanadium is a shape shifter. If you add or remove electrons from its atoms, the element's electrical charges will become more positive or negative, and its and its color changes from purple to green, blue, and yellow. The metal's rainbow color palette led Swedish chemist Niels Gabriel Säfström to name the element after Vanadis, the Scandinavian goddess of beauty. There you go. But vanadium's ability to change its color is what makes it useful in a battery. Here is how it works. One tank holds vanadium with a more positive charge, while the other tank holds vanadium with a more negative charge, which is just like a battery. You can think of them like the plus and minus sides of the batteries, anodes and cathodes, sitting in a TV remote or a flashlight. Vanadium flows through each battery cell on either side of the membrane, which is why it's called flow battery. So you are actually flowing vanadium itself and not just electrons as we do in batteries. All of these tanks are lined up in pairs, positive, negative vanadium. Positive here, negative there is a battery, so vanadium tanks with positive and negative ions. Cute as hell. Every tank is hooked up to a set of pipes, so you can flow the vanadium as needed. The pump then here every tank is hooked up to a tank with to a set of pipes that pump vanadium into battery cells stacked in cabinets on the floor. So there is a cabinet under the floor that pumps vanadium into the battery cells, and here are the battery cells that are actually the standard battery cells. So here is a battery cell. There is a membrane, positive and negative charges, so vanadium with positive here and vanadium with negative here. Very different than a standard lithium ion battery where you charge the battery, store the positives on the anode side, negatives are not there, but you have an electrolyte and you connect the battery to a cell phone or so. The electrons flow, provide electricity, and then are depleted and end up on the cathode side. Then they have to be moved back by charging or recharging. When HAPCO network wants to charge the batteries, it uses energy from the wind turbines to move electrons from the positive side of the membrane to the negative side, which creates an imbalance. Now there are a lot more electrons crammed into the negative tank than the positive tank, and they are itching to spread out evenly once again. When HAPCO network wants to use the energy stored inside the batteries, it lets electrons flow the other way. Their movement creates an electric current that can power homes and businesses across the island. Flow batteries are designed to tap giant tanks that can store a lot of energy for a long time. To boost their storage capacity, all you have to do is build a bigger tank, add more vanadium. That's a big advantage. By contrast, there's no easy way to adjust the storage capacity of a lithium-ion battery. If you want more storage, you have to build a whole new battery. Right. Flow batteries in this plant are designed to store energy about 4 hours, which is on par with lithium-ion batteries if you use it continuously. But Sumitomo Electric says it expects future projects will aim to double that duration to 8 to 10 hours. That's about what they would need to last overnight when solar panels are dormant, or to fill in the gaps between gusts of wind. Fantastic news. One major barrier to building more of these battery farms is finding enough vanadium. 3/4 of the world's supply comes as a byproduct from 10 steel mills in China and Russia, according to Rodby, who got her PhD at MIT, Massachusetts Institute of Technology, studying the design and market for flow batteries. Australia, South Africa, and the United States also produce vanadium, but in much smaller quantities, and if they get a hang of flow batteries, they're not going to export it, they're just going to use it. But I'm sure people are working already on replacing vanadium with something else that will be much more abundant or locally available. Mines that have been proposed could boost supply, and some flow battery startups are trying to sidestep the vanadium problem entirely by using different materials that are easy to buy, as I said. The other hurdle is their upfront cost. Vanadium flow batteries are at least twice as expensive to build as lithium ion batteries, Rodby said, and banks are hesitant to lend money to fund an unfamiliar technology. Socio-technical transitions are difficult for many reasons, and funding is always a top reason. But experts say flow batteries can be cheaper in the long run because they are easier to maintain and last longer than standard lithium-ion batteries, which might have to be replaced after 10 years. But Rodby says flow batteries can last much longer. There really is no finite lifetime for a flow battery in the way there is for lithium-ion, Rodby said. Sumitomo Electric President Osamu Inoue said his company guarantees his flow batteries will last 20 years, but the vanadium inside can be reused forever in future batteries. The company's oldest commercial batteries have been running for 11 years so far. Okay, here is the flow batteries on Hokkaido connecting to homes, businesses, power plants all over the island by plugging into the power grid. Ugly mesh of wires. Every time you go in a nice forest and you want to take some picture, there are cables blocking the view, right? So how does the grid work? Wind and solar power are coming. Batteries can keep them from causing chaos on the power grid. Just outside the building that houses the gleaming floor-to-ceiling tanks, Sumitomo has built a new version of its flow batteries, this time tucking all of their components into shipping containers. That makes them faster and cheaper to build than the 100 million indoor demonstration plant next door. The batteries connect to homes, businesses, and power plants all over Hokkaido by plugging into the grid, which is the caption that I'm rereading. Power lines running from the flow battery plants in Hokkaido. So I know this is getting a bit long, but it's a newspaper story, so we'll just read it. These batteries help Hokkaido keep a steady balance between the amount of energy its power plants generate and the amount of electricity its homes and businesses use. But there's not only this, they are not the only way to maintain that balance. While Hokkaido is on a battery building spree, it's also beefing up undersea power lines to share electricity with the rest of Japan. So how to transmit that energy? So far, it's working. Even though Hokkaido gets nearly a fifth of its electricity from wind and solar, it doesn't face blackouts and it wastes almost zero energy. Having a stable grid allows Hokkaido to keep building more renewable energy, bringing it closer to its goal of cutting power plant emissions to zero by 2050. The flow batteries sitting in the shipping containers outside Sapporo paved the way for HEPCO Network to add 15 new wind farms around Hokkaido. The turbines generate about 3% of the island's electricity without pollution. Experts say the world will need to build many more batteries like these to stay on track to cut greenhouse gas emissions to zero by 2050. Over the next 6 years, utilities will have to build 35 times as many batteries as there are today to soak up all the extra renewable energy that will come online, according to the International Energy Agency, IEA. The point of all this battery building is on display off the coast of Hokkaido. Earlier this year, Japan's biggest offshore wind farm opened just off the coast of Ishikari, a seaside town on the outskirts of Sapporo. The 14 turbines, each about 20 stories tall, face across the water from a natural gas plant that would shut down if Hokkaido's clean energy plans succeed. So here is Japan's biggest offshore wind farm site just off the coast of Ishikari, a seaside town in Hokkaido. Okay, so again, newspaper story, good story, and good news as well, because it should be possible to repeat the flow battery technologies everywhere where there is solar and wind potential, and storage is always going to be required there. Of course, vanadium will probably be a limitation if everybody starts doing this, but already new materials are being searched for, and you can be sure that considering the economic and other incentives, there will be new technologies. Lithium-ion batteries themselves are now constantly being chased by other technologies like sodium battery, solid-state batteries instead of liquid electrolyte, air batteries, and so on and so forth. So vanadium replacement will not be too far away, I'm sure. Okay, so it's a cute technology called flow batteries that we learned about from a newspaper article, but it's very useful. So see you in the next topic.